This is lesson 6.1, solving linear systems by graphing. This is the first lesson of chapter 6, which is solving linear systems. In this chapter, we'll build off what we've learned about linear functions, graphs, and equations in order to solve problems involving two functions. First, some vocabulary. We already know what linear equations are. These are equations that represent linear functions. And in the last chapter, chapter 5, we learned the three different ways to represent linear equations. We have the slope-intercept form, the standard form, and the point-slope form. What's new is a system of linear equations. This is two or more linear equations with the same variables. So for example, 2x plus 3y equals 4 and 5x minus y equals 1. These are both linear equations and they have the same variables. So together, this is a system of linear equations. Systems of linear equations represent a problem and can be solved in a few different ways. And we'll try to learn this looking at our case study below. So imagine you're getting a new phone and a new phone plan, and you're comparing different companies. Kudo's offering a phone for $700 up front, and then a monthly plan of $50 per month. On the other hand, TELUS is offering a phone for $525 with a plan of $58 per month, which is the better offer. So we can represent this with linear equations. Our variables would be X represents the number of months you would have the phone for, and C represents the total cost you would pay. So here are the two equations I came up with for each company, Kudo and TELUS. So for Kudo, you pay $700 up front and then $50 for every month that you have the phone. Whereas TELUS, you pay $525 up front and then $58 for every month you have it. But the question is, how do we compare these two equations? How do we actually know which one is the better offer or which one is cheaper? So we might look at a couple specific examples. Let's say you only have the phone for 2 months, a very short amount of time. In that case, TELUS is actually cheaper. And I showed that here because I took each equation and replaced X with 2 because you have it for 2 months and solved. So for Kudo, you'd pay $700 right away and then 2 months at $50 each for a total of $800. But TELUS, with the same logic, you'd actually only pay $641 for those 2 months. So if you have it for a short amount of time, TELUS is cheaper. But what if you have the phone for 30 months? That's just under 3 years. It's like 2.5 years. In that case, Kudo is actually cheaper. With the same logic, I replaced X with 30, and I found that Kudo would be actually slightly cheaper over 30 months than TELUS. So yes, this is helpful information, but what if you have the phone for 20 months or 25 months? Are you going to do this calculation every time? You don't know how long your phone is going to last. So how can you actually compare which plan is better? And this is where systems of linear equations come in handy. A solution to a system of linear equations is where the equations in the system are equal to each other. And there's many ways we can find this solution to the system. Today, we're going to learn how to solve it using a graph. And then in the next 2 lessons, we'll learn how to solve them using algebra. So a graphical solution to a system is where the two equations intersect each other on a graph or where they cross. And there's 3 situations when you have graphical systems, 3 possible solutions. The most common would be to have one solution. This is when the lines would intersect once. So maybe one line goes like this, the other one goes like this. You have one intersection point. There's one possible solution for this problem. The kind of special cases would be no solution. This is when the lines never intersect. So we'd have parallel lines, which we're pretty familiar with at this point. There's never a situation where they cross each other, so there's no solution to that problem. You could also have infinite solutions. This would be when the lines intersect at every single point, or you just have identical lines. They just cross each other at every single point, so there's an infinite number of solutions. So going back to our phone example, if we try to solve this problem, we could graph both equations and see where they intersect. So that's what I did here using a computer program. Red is TELUS and blue is Kudo. So what we can see is that they intersect approximately at X equals 22. So after 22 or at 22 months, TELUS and Kudo both cost the same amount of money. But before 22 months, the blue line is higher than the red line. So Kudo is more expensive than TELUS if you have it for less than 22 months. But after that intersection point, they switch. Now TELUS is more expensive than Kudo if you have the phone for longer than 22 months. So this graph has a ton of very helpful information for you because you know at exactly what point one of the companies will become more expensive than the other. So if you're someone that goes through phones very quickly, maybe you drop them a lot, you might want to go with TELUS because you know you'll have it for a smaller amount of time. But if you're someone who wants to keep your phone for many years, then it might be better to go with Kudo because over time you'll actually spend less money. So some other examples, not with context, but some other examples of solving systems are below. We want to solve this system by graphing. So the steps are, first, you want to convert it to slope-intercept form if it's not already in this form, because we want to graph and we know how to graph easily from slope-intercept form. We take our two equations and we convert them to slope-intercept. This is all chapter 5 material, so you should feel comfortable with it. I have my equation in red and green. The second step is you're going to graph them on the same grid, which I've done here. And again, you should feel comfortable doing this because this is all chapter 5 material. So I've color-coded it just to make it a little easy to see. But the really important thing that we want to look for is where these two lines intersect, if they intersect at all. And I've circled it in blue that there is a point of intersection at the coordinate 2, -3. So that means there's one solution to the system, and that solution is 2, -3. And that's it. So yes, you can apply context to these lines like I did with the phone problem, but sometimes you'll do problems that just have numbers and letters, and you're just looking for the point of intersection. Here's another example. So we have two systems. We want to solve it by graphing. First, we convert each of these equations into slope-intercept form to make it easy to graph. One is in red, one is in green. Second, I graph them on the same grid to try to identify where their intersection point is. On this graph, they do not intersect. But maybe if the graph continued, they would intersect later on. You don't really know. But if we look closely, we'll see that the slope of both of these lines is the same. It's 2/3 for both of them. So we know that these lines are parallel, and that means that they'll never intersect, no matter how far off we extend these lines. So that means there's no solution to the system. There's no situation where these two lines will intersect, no situation where these two lines will be equal to each other. And this is the last possible type of solution you could have, which would be infinite solutions. So we want to solve the system by graphing. Just like before, we set up both equations and we convert them to slope-intercept form so that it's easy to graph. Right away, you might notice that these two equations are identical to each other. So if it's asking you to solve by graphing, you do need to still graph. But once you do so, you realize that they're the exact same line and they overlap at every single point. So that means that there's infinite solutions to this system because these are identical lines. Because you're asking, when does this line equal this line? Well, at every single point. They always equal each other because they're the exact same thing. So therefore, there are infinite solutions. So in terms of solving real world problems, if you were trying to solve a problem and you got no solution or infinite solutions, that's not very helpful because you don't have an actual concrete answer to go off of. So that's why most of the real world problems that we would look at would have one solution, just like our phone one did, because there would be a situation where they do cross each other. So this is how you solve systems of linear equations with graphing.